Hello and welcome, my name is Trismegistus, and today we're going to be reading through and speculating about the latest Factorio Friday Facts. Friday Facts 390, Noise Expressions 2.0, posted by Erendel and Genis. So I am just going to say, this is a very technical one. It gets even more technical as it goes along, so if that's not your cup of tea, then no harm, no foul. Feel free to skip around. But yeah, I will be reading it all out. Some of it I'll be trying to explain as best as I can, but it will be quite a techie Friday Facts. Hello, we've had a lot of requests to talk about map generation. It's difficult to talk about map generation without first explaining noise expressions. From time to time, we need to talk about noise expressions anyway, because they're a critical part of the game, but I don't think we've ever done a very good job of explaining what they actually are at a high level. We will take a closer look at map gen again in the future, but for now, this will introduce the basic concepts and act as a primer for later. What are noise expressions? By Erendel. The expression part. When making a game world in Factorio, you need to decide what gets placed where. All you really have to work with is the X and Y position. The terrain generator can't know anything about what is already placed. Somehow, you need some code that converts X and Y into the type of tile to place, and which trees, rocks, resources, decoratives, cliffs, or enemies to place on top. So that's just expressed in this figure here. I got it a figure, and it is actually a figure this time. But basically, this is showing the different types of bits and pieces that need to be considered when you're trying to generate a map in Factorio. So you've obviously got X, Y as the coordinates. You've got the terrain type. So you've got your grass, your sand, your desert, potentially concrete if that's been laid down on a pre-existing map. You've got cliffs, this is all the resources, iron, copper, steel. I did wonder, and there may well be like a hidden thing in here. This looks, I don't recognise this red one, but I wondered if maybe it was the lava. But you got the uranium, coal, it could be copper I guess, because we've not got copper otherwise, iron and stone. The orangey one didn't look familiar to me, but it could be copper, I say it could be lava, something like that. You then got rocks, which is just the random rocks rather than the cliffs. You've also got fish when you're putting in the sea. I think this is meant to represent sea rather than kind of just the fish themselves. But I guess they do need to be placed. You've got the biters, you've got terrain decoratives, which is the little bits, tufts of grass and stuff you see on the map. And then you've got trees. And they all need to go in and basically be placed somewhere in the world. Obviously, there's slightly different things going on with each of these when you think about it. You don't want your resources too close together, or you want to be able to control them, certainly. And you don't want them to be distributed in the same way that you would cut out, a terrain area. And like cliffs are these long features, whereas resources need to be big splats of resources. So there are different rules and different things you want to achieve with each of these different types of placement. So just to explain what they're kind of getting at here, it's sort of basically when they say that, it can't know anything about what is already placed, basically they don't want a map that says, right, what's next to me, and I'll place something in relation to what's next to me. They simply want to go around and for every coordinate, because Factorio, although it looks like it's 3D, is a 2D game. So it's all a flat plane and just everything has an X and Y coordinate. So when they're placing these things, they're saying they want to have a value or a flag or something like that says place this type of thing on this exact coordinate. So this X, this Y. And they don't want it to say, right, well, my neighbour is doing this, therefore I must do this. My neighbour is doing this, my neighbour must do this. You can generate maps that way, and you can generate terrain that way. But they're saying they just want to have a fixed set of coordinates that dictate what happens on that exact spot. And obviously then they can modify that neighbours, so the or being close together by having similar values. So they're all 1 for or sort of thing, or an or value in that area, and they just want a function that defines that area and gives it a value, and then the game can just store the value basically. The middle of the map, where X and Y are both 0, is the origin and the starting position. We always want this to be land, otherwise you're stuck in water. We can calculate the distance from the origin to get a distance cone and use it to make a circular island where everything above that some value is land, otherwise it is water. So then we got some diagrams basically showing, what they're talking about. So when they talk about origin and 0, 0 as the XY coordinate, what they're essentially saying is that when you spawn on the map, that's the origin. So where you as the player character are is 0, 0, and then it's a Cartesian coordinate system basically. So X axis and y-axis, and any coordinate that you have, either be positive or negative, will define a position on that Cartesian system. So that's then what they're showing here. So what they're actually doing, as it happens, is converting it to a radial coordinate system so that it can do a lot of the maths that it needs to do, and then obviously it's converted back because these circles define values, and then those values can be assigned to the particular XY coordinate is basically. So that's kind of one of the things that's happening here. The other thing just to note, this is Pythagoras, basically, if you know the Pythagorean theory. Basically, this is it's actually a 3, 4, 5 triangle, which makes it very easy to know. This distance is 3, this distance is 4, and therefore this distance must be 5 because it's a right-angled triangle, and therefore it must follow that 3, 4, 5 rule. And this is the Pythagorean equation, basically. So it's normally expressed, distance squared. So that line basically is the square of those two lines. If you never understood how that works, basically what it's saying is that the square, if you literally turn this into a square, a 3x3 square, this into a 4x4 square, and then you would have, as I say, a 5x5 square here, the area of this, which is 9, 3x3, and the area of this, 16, 4x4, is the same as the area of the square on this side that you would draw, 5x5, 25. So 9 plus 16 equals 25, and 25 is the area of that square. And that's basically what Pythagoras' theory is that when, if you draw a square on either of these, then for this type of triangle, these add up basically, and they have the same area, and that's effectively what a square is. That's why it's called a square. What they're doing here then, distances are, did I read that? Use of x and y to get the distance from the origin, so basically that. So distance is a radial gradient that increases away from the origin, dark is a low and light is a high. So once you do this, you can work out a distance for every single point, xy point on this grid. And what they're saying is that what they've done is that for low numbers, and there's obviously some sort of 50-50 point, but low numbers are dark, so the origin is going to be black. And as far as infinity, so as far as you could possibly get away from, it would be white. Obviously, you can't really reach that. And that's just to show you what's going on, really. So all of these distances are further out. They're given a particular value, either on a grayscale from sort of 0 to 1, basically. Number 3, if elevation is then set to the inverse of distance, then land gets lower further away from the origin. We can add 100 so that the origin is above 0. It can help to think in 3D to see the resulting cone. So inverting is literally dividing 1 by the thing. So if you invert 1, it's 1 divided by 1, so you get 1. If you invert 2, it's 1 divided by 2, so you get a half. If you invert 3, 1 divided by 3, it's a third, so or 0.333 recurring. Then you can do it with 4, 5, any number you can do. So what they're saying is that if you went out, say, 100 distance, then 1 divided by 100 would be 1 over 100, so 0.01, which is very small. And essentially, therefore, distance can be very quickly converted into height, because you can say that this is the highest, the origin is obviously the highest because it's 0, and the further away you get, the lower it goes, and that's what this cone is. It's a bit exaggerated. What they're also then doing is offsetting, basically. So by adding 100 to every single value, so so it's not 100, it's not 1 at the origin, it's 100, and out here it's not a tenth, it's 100 plus a tenth, and that just lifts everything up. They're then showing this blue plane, and if you imagine this is this water here, you can kind of see what's going on. So the water line tends to be at elevation 0, so they are artificially defining a water line by saying that it's 0. If you think about it, that math is a bit weird, but basically there's a point above which you say that's land, and below which you say that's water for those values. So land elevation is greater than 0, and water elevation is less than or equal to 0. They're basically then flattening it. So the cone helps you imagine it, but really what's going on here is it's just a threshold, basically. So at a certain level of greyness, a threshold is set, and that's the point above which land is there, and everything else is water. So that's all they're really doing. Images are not to scale, it notes as well. Although we don't always need to change the probability of both tiles at once, we only need to make sure that the tile we want has the most influence where we want it. For example, Land could always have a weight of 1, and then water could have a weight higher than 1 when we want water to appear. So it's basically flipping it on its head, essentially, from what I just said. So you would say land is 1, and if we give every other piece of terrain around it, these blue ones, because remember we want to store it as an XY coordinate. So we say if this XY coordinate is 1, it's land. If it's more than 1, after we've done this math, then it's water. Okay, so that's the thresholding going on again. If we can add values to the x and y coordinates before it goes into the distance function, then it shifts this cone to a different position. Offset cones could be used to make new islands, or add a section to the existing island, or invert the new cone to take chunks out of an island. So this is just if you offset. So if you say, right, my origin is actually up here, so it's 3x and 3y, then do this same process, then you'll get a differently positioned circle. And you can also obviously add higher offsets, to the height. So if it's higher offset number, then you get more terrain because that cone is higher up, basically. And also, of course, you can just invert everything and say, right, well, if we literally do that 1 divided by the number thing again, it turns into water. So where it would be us drawing a piece of land, we're now drawing a circle of water. This is really like the absolute basics, basically. It's a bit odd, this blog, I would say. In that it explains these basics really well, and then suddenly flips into and I'll give you a heads up if you say not too interested in the super technical stuff. I think this is a really good explanation of the basics, but then I say it'll just suddenly flip into really complex, and there'll be bits of code and stuff like that. So you'll have to kind of bear with that, and I'm not going to delve too deeply into that because I know it's a bit more specialist. And saying that, it does sort of make a little bit of a leap here, as it doesn't really explain quite what it's talking about, but we also have most of the arithmetic operations, like absolute value, modulo, exponents, and trigonometry functions. The trigonometric functions can be used to rotate positions instead of just using offsets, and that's the main trick to the starting areas of Volcanus. I'm not going to explain these, so these are basically different mathematical functions. So what it's saying, essentially, and you can kind of understand it quite easily if you think about it, in terms of these shapes. So if you've got this function that says draw a circle, then you can apply more complex functions to it to distort that circle, essentially. So, rather than draw a circle in here, it becomes a bit wiggly and wobbly because you're applying various other functions to it, or you're getting it to add on smaller circles or chop off smaller circles. And you can imagine building up an algorithm, so a mathematical set of functions, mathematical set of operations that will define a wiggly blob, and that wiggly blob you can use to draw terrain, either by filling it in for sort of a patch of ore or something, or taking the edge of the wiggly blob in order to draw a cliff, or I guess a lava thing. And then obviously, as I say, if you set the values lower and higher, you can change them into lava cones and all this sort of stuff. And you can also imagine, maybe you set the ranges of values, so you could define different terrain types by either overlaying a separate function going on or using the same function, and sort of saying that values between 1 and 2 are grass, between 2 and 5 are sand, and between 5 and 10 are water. So you can imagine, as you build in more complexity, you get a more detailed and more complex map. The core part of the expressions is that we can chain these operations together for things like test1. And if you think of test1 as being just a result, a function, if test1 equals a plus b times c, and here you would be replacing values, you put in 5 and 6 and 7 as a, b and c, and you would do the maths basically. But we can also make one monoise expression reference the output of another. So for example, test doubler equals test1 times 2. So test doubler then, if you imagine that multiplied out expression, and I say this is kind of explaining algebra basically. So as I say, it's a strange sort of way of explaining it rather than just saying what it is. But basically then test1 is twice the value, and it's always twice the value. So whatever numbers you plug in for a, b and c, test doubler will always be twice that. And so you can basically, this is one of the ways you optimize code, by basically having a thing that references something else and is always double the value. You don't have to do the mathematical function of doubling, basically. So instead of having that math done every single time that you want that operation done, you simply, you could always store them, that would be even quicker, but, then you'd have memory issues and stuff like that. But basically you have something that says, right, that's always double, and it has inherently done that maths, already when it calculates it, or somebody simply uses a referencing system. But basically you don't have to do all of that maths every time you want to double value. You can just refer to that one. Okay, so all of this is great. You could make an interesting crop circle pattern with this if you wanted to, but it's not great for a natural landscape. For that, we wanted some noise. And this is literally, it does look like a crop circle. I don't know if people are... I think people still make crop circles, don't they? But it was a big thing during when I was a kid, basically, that, there were all these crop circles and, was it aliens and all this sort of stuff. And it obviously wasn't. It was students, basically. But yeah, people go out and flatten crops in circles. And eventually they started making really complicated design. The noise part. In terrain generation, noise does not mean sound. It just means random numbers. When making random numbers, your most basic setup is to generate completely random numbers every time you need one. This is called incoherent noise, and no point has any relation to any other point. If zoom in, you just get more complete randomness, so the usefulness is quite limited. You don't really get it so much now because digital TVs have kind of taken over, and I guess a lot of radio is like digital radio and stuff like that now. But basically noise, it's called noise essentially because it's static, and it is literally, I know that it says it doesn't mean noise, but that's the origin of it. Basically it's sound essentially. When you have a detuned radio, as I say, older televisions, if they weren't tuned to a channel, then they would pick up noise. We've all lost the opportunity to make the interesting scientific point that the noise you pick up in your TV is actually the cosmic background radiation, and so what you're seeing effectively is that the Big Bang essentially. You can go and look at lots of science videos to watch that, but the basic point is it is completely random. It's otherwise known as white noise, and it's literally just completely random. A computer can't actually properly do random. Because of how computers work, because they're calculating machines, they can't really do random, so they simulate randomness, and they're not always that great at it. There are actually companies that provide random numbers because biological processes are random, and you can real world processes are often random, and you can therefore use those to generate proper random numbers. That's just another weird aside. But basically, what the point is that because it's so random, if you zoom in, you just get more random. There's no structure to the randomness. And this is going back to that point I said before about, a design randomness or a sort of functional randomness rather than complete randomness. You might be able to say, right, well, these are all one because they're all close to this position. And so when you zoom in and out, you just get a bigger version of that. You don't just get more and more randomness because, noise is, proper random noise is like fractal, effectively. You just zoom in and it's not fractal. And these other algorithms are, so that when you zoom in, you get similarity, like growing similarity. I'm not sure that's a very good explanation, but it gets the point across. Coherent noise is different. It makes good use of the x and y coordinates so that nearby positions can have similar values. This means that as you move over the landscape, things change smoothly and coherently. The main coherent noise we use is basis noise, a Perlin-style noise, which is described in Friday Facts 112. The output values end up with an approximate feature size. If you zoom out, it's indistinguishable from incoherent noise, but if you zoom in, making the features larger, then everything keeps smoothing out until it's almost flat. And that's being demonstrated here. So this is the zoomed out version, and as you can see, it looks pretty much like, it's zoomed in from that, but it could just be a zoom in on it, any old part of it. But the point is the more that you zoom in, you see how you start to get this coherency of things. So in this random noise, if you zoomed in and in and in, it would just keep looking like itself. It would just be continuously going closer and closer. But here you've got, structures emerging essentially. And they're structures because they're similar location and they're given similar value. And then as you zoom even more in, this gets very blurry, but I don't know if you can see, but there are blobs basically, and they're even bigger blobs the more you've zoomed in. So in other words, it stops getting this speckly pattern and starts showing bigger structures. And essentially their point is, and they do explain it, is that you can use, if you set one of these thresholds, so a bit like this, if you set a threshold and say, right, any value above this is land, any value below this is water, or the other way around, depends how you want to do it, then you would imagine converting this, at some point in this grayscale. I mean, if imagine this was proper black and this was proper white, but these blacker bits might become land and these whiter bits might become water. And you basically say anything that's above this particular value on the grayscale or below, or whatever, then you convert it to land or water as appropriate. And so you can say, well, we'll come on to, I'll read it through, but you can imagine using that process to basically create solid shapes, bigger shapes, but that are randomly crinkly on the edges effectively. This is great because we can use some noise with a huge feature size for continents, a medium size for islands and bays, and a smaller size to break up the coastline a bit more. And that's sort of what you can imagine these becoming, basically. So this becomes continents, this becomes islands. This is then used, to dig bits out of the edges to make it look a bit more organic. This is the basic idea behind fractal noise. Multiple levels of... maybe I read that and that's why I said fractal. Anyway, multiple levels of different sizes are added together, with smaller layers having progressively less impact as they add smaller details to certain areas. In other words, the strength of them is changed. So the fact that this is solid blobs, you don't take it all off. You don't eat completely away at the terrain. You just use it where the value is close to zero anyway, type of thing, where there's a transition, and you can just use it to modify the edges of things, and maybe occasionally take the little chunk out. But it's sort of a cumulative. Basically, so if this is 1, 0 and this is 0.5, 0.75, then this would be 0.125, and smaller increments of like effect being applied. And of course, going back again, these are individual coordinates. So what you're saying effectively is that this individual coordinate, it's this plus this plus this, and that gives a single value, and the game then knows to convert that. All right, that means it's land, and that means it's, sand for land, and that means it's grass land, and that means it's coastal water, and that means it, do you see what I mean? So you can create an array, basically, of numbers that the game can convert into different types. The next type of noise is spot noise. It creates a number of spots on the landscape with a certain amount of spacing. This is what we usually use for resource placement. Each spot is actually a cone, so we can have a higher richness in the middle of each patch. The resource cone is then perturbed by adding some basis noise, so it's not such a clean circle. If you want to read more about spot noise, I recommend checking out Friday Facts 258. So this is what we're showing here. We've got these lovely slidey diagrams in this again. So left, which is this one, Nauvis resource cones before the added noise to break up the circle. Right, Nauvis map as you'd normally see it. And you can literally see... So this iron is actually a really good example. And if you can see at the bottom, where I've roughly got my cursor, basically as you move it back and forth, you can see that the spot noise has been generated blob, and it's a cone, and so that's why we get higher resource values at the center and lower resource values at the edge. But obviously you don't just want circular blobs on your map, and so instead on top of that they apply this basis noise, the purlin type noise, the same noise as up here, to give it a crinkly wobbly edge basically. And these all match up basically, so you can also see that's why you get, because it's a completely independent function and it's not looking at the terrain generation, that's why you end up with like that copper patches across the edge of the water, because it's just picked a spot and that happens to be on it. That one there, the iron, is in the middle, and what you can actually I think there is actually terrain on that island, resources on that island, but you can imagine it would pick spots in the water as well and just sort of attempt to put them nowhere basically. Putting it all together, the real power comes from artistic control over these things and finding the maths required to do it efficiently. Here's a couple of examples. Spot noise is not just for resources, it can also be used for volcanoes. We add huge spot cones to the elevation to make the main volcano body. We can also invert the cone and min the tip to invert the mountain peak for a lava pit. This figure is just showing it basically. So they create this spot. Now they say huge because if you go look at this, if you imagine that's their normal spots, that is the spot they're talking about. So it's gigantic compared to this spot. So they've simply just increased the size of the spot. And then when I was talking about the basis noise being used to just chip away at the edges. And clearly they're also doing something where it then takes that shape and kind of does inner iterations of it, and that's how they get the concentric lines to make it look like a volcano. Obviously it's all flat, really, it's just an optical illusion, but that's how they're creating the height that defines where they are. And then to create the actual the caldera, the bit in the middle of the volcano, the lava, they then literally take that same mountain, invert it, so multiply by -1, and then give it an offset, basically, so punt it up, essentially. So this shape here, gets punted up to become and then they just literally say, right, well, where these two overlap, this then eats away, and that's where we get lava. There must be something that either says, liquid above a certain height is then made into lava or something like that, or maybe they use it to define an edge and say everything inside is lava. Because if you think about it, this height value here is the same as this height value here, but it's not going to put lava there, and it is going to put lava there. So there must be some other function that's running to basically decide that is lava rather than another. These sorts of inversions are critical for some things. If you want to have a mostly water map, you can just reduce the elevation, but this would tend to make islands. What if you want a mostly water map, but you still want most of the land connected? For this, we can use absolute value and bounce any negative value to be positive. If we then invert it, all of the values are negative, but a small addition bumps a narrow band into the positive region. This makes a series of narrow land paths that almost always connect. We use this sort of pattern in the volcano's lava area to make sure that there are always paths through the maze. So you remember it said about having the arithmetic functions, basically. So absolute, that's a sine wave. So I'm not going to explain that, but it's a regularly repeating wave, and it just goes up and down, up and down, up and down. Here it's based around the origin, so as it goes through 0, so it goes from positive to negative to positive, and it does it on a very regular frequency. What you would then do is use absolute, and absolute essentially takes away the negative value. So where this is -1, it's just turned into 1. So what it basically does is says, if it's a negative number, multiply it by 1. If it's a positive number, don't, basically. So you then get a bouncy function. What they're then doing is they're minusing that. So they're then multiplying that by -1. So every time it's positive up here, +1, it becomes -1. Now you could obviously do the negative absolute effectively, and that would just quickly achieve the same thing, but it's just easier to understand if you do them as separate operations. So you get the negative absolute value by doing those two operations. What you then do is you use this offsetting again. So this offsetting and this offsetting idea here. So you just move it up, okay? And what you have to think is this is in 3D. So if these are circles, effectively, these are cones, yeah. Then by doing this whole flipping around and moving up around, you're going to get edges to the cones. And I say they're not because they use the noise and make it all wiggly stuff. But you're going to end up with that same idea that the cone, you've just pushed the edges of the cone up. And so now it's got like a ring, basically. So effectively it's a way of creating, if you imagine this wasn't filled in, it would create a ring pattern and a whole series of interlinking rings. And of course it doesn't look like that because they apply the whole noise and the wiggle and the wobble and all that sort of stuff. And that therefore means that you're getting these connected paths, so you aren't going to get trapped. Or I suppose there probably are places where you can get trapped. We know it creates little circles of cliffs, for example. But basically it ensures that these cliffs don't really touch together and you can walk through them. Because imagine how frustrating it would be if every time you tried to walk anywhere, you had to keep going back and forth and back and forth and back and forth. So that's what they're trying to avoid. Noise Tools by Arundel. Before joining Ruby, I was working on new planets for my space exploration mod, and still am. In space exploration, each planet type will have a unique map generation, a bit like the planets in Space Age. Making just one completely new planet is a huge amount of work. So when embarking on making 14 plus new types, I decided to invest in making some new tools to make the process easier. This resulted in my own set of noise tools that do a number of things. They auto-place cleaning so that testing is much faster. They have planet switching presets to be able to preview other planets. They have a convenient inline way to add temporary debug sliders so that noise expression values can be adjusted from the map preview screen. And last but not least, the ability to use the map preview to visualize noise expressions output directly. The last one, about noise visualization, is the one that is really difficult to do without. Without it, you are very detached from the output of the system. Let's say, for example, you add some new code that is supposed to make some of the existing sand on the map go from a yellow version to a red version. You load up the game, wander around, but you don't see any red sand. What went wrong? It could be any number of things. Maybe it is actually working, but coincidentally, the areas that should be red happen to be underwater and grass instead of sand. More likely though, if you've explored a large area and you still didn't find any, then it's probably broken somewhere. But where? The noise visualizer lets me choose a specific noise expression and convert that to an image in the preview screen. That way, I can see things like the distribution and output values of expressions to say things like, the scale is way larger than I thought, so you'd need to go 10 kilometers to find any difference, or the output range is too low and it's never strong enough to make a change. Or maybe one value accidentally goes negative, multiplies with another negative, and causes some other weird, unexpected problem. So when they talk about, when they're talking about noise expressions, it's basically this. These are the expressions, essentially. So these are like the more complicated algorithms. So if this is the basic function of, do noise, do noise that zooms in, do spot noise, if those are some of the basic expressions, and there are clearly more, basic functions, as it were, then by bringing them all together, that's where you get the noise expressions, basically. So that gives you the algorithm that says, right, well, when I'm building terrain, on a distance-based thing, this is the function that I always use to do it. That gives me the values, and the values then remain the same because, they could do, but they're not going to change that dynamically for the map. I say they could do, which maybe we'll get that in a future map. There's a sort of a hint that maybe something like that might be coming, but anyway. But yeah, so what Arundel is then saying is you could do that expression, you could have that function doing that to do that thing of, right, we'll change some of this yellow sand to red sand. But if you mess it up, or you get it wrong, or the maths doesn't quite work, or you've called the wrong bit, or it's essentially a debugging tool he's talking about, but it's like a visual one, and you can use the map preview generator using this heat mapping. It actually reminds me, I'll be honest, these look, I was talking about fractals, like this was what I had, what I was mentioning it, because when fractals were kind of, I don't know about discovered, but like first popularized, as it were, you used to get these like hippie style LSD trip sort of, pictures of fractals where they would color them in with these really radical, extreme color variations, going from bright reds to bright greens to bright blues and all this sort of stuff. And that's effectively what this is. The idea is it's a debug tool, basically. So this is what the map looks like. Okay, this is the plain thing, but it's so plain in a sense that you can't really tell what's going on. And you remember there's this thresholding going on, right? Well, this shows you the exact values, and the colouring helps you understand what it's, like chunks of values, effectively. So this, you see all this subtle detail that's going on here. I'm guessing this is trees. Let's have a look. Oh, it's not trees. Okay. Maybe it doesn't do it for trees. I guess because they're overlays, because it's not showing cliffs either, is it? So they're obviously a different way of doing it. But effectively, you've got this thing that's saying, right, all this tiny, tiny level of detail, it doesn't actually show you on the map because it has a threshold, and it basically says, right, well, all of these are between the value of, say, 0.7 and 0.9, right? And it's got loads and loads of wiggle in it. So 0.701, 0.702, 0.704, 0.709, all that tiny, tiny wiggle is expressed in the algorithm. But then the game comes along and says, right, everything between 0.7 and 0.9, dark brown sand, okay? And you can't really tell the subtlety of what's going on in this because that detail is hidden. And this just expresses it, okay? And particularly, it's very useful for the water, or very clear on the water. You see how it's got this darker blue, lighter blue, and all this little detail. And you see how there's like a little island there, and a little island there, and an island there, and an island there. And you can kind of see that those are clearly, either the peaks of these cones effectively, and that's where all that detail is coming from. I'll be honest. I mean, he does say, and he's probably. I mean, I'm sure he's right, but it would be unplayable like this. You'd kind of go blind probably. But I don't know that if they want to whack this on a poster or something, I wouldn't be averse. It does look amazing, and so they're always used to those pictures of the fractals from back in the day. But yeah, I could stare at things like this for hours. Anyway, so the caption says left Nauvis map as you normally see it, right Nauvis elevation. Blue is elevation below 0, with darker values being deeper. Yellow is high, green is very high, used for water and cliffs. So green must be the very high, so it's got the cliffs. Okay, so that is how they draw the cliffs. Interesting, because it does sort of match some of the edges when you look at where the cliffs are, ish. This really shines when working on things like multiple biomes. Usually, if you just rely on the tile change as an indicator, you can see that a change happened when going from one biome to another, but you can't tell what the rate of change is like. So that's what I was saying about the edge of the gradient. With this version, you can sort of tell that this is building up to the values here and here and here, and that there's a gradient going on across here. You can't tell that at all on here. I mean, you can kind of because it's that there, but these bigger blob areas, you just wouldn't be able to tell what the detail was. Often, a soft rate of change is better, so vegetation can fade out as things get drier. But usually, there's no way to see that ahead of time. With the visualizer, you can tell if the biome transition is hard or soft because it can display up to 255 different values, 255 different colours basically, and show you the gradient. Left, volcanoes elevation. Blue is elevation below 0, with darker values being deeper. Yellow is high, green is very high. Right, volcanic temperature. Black is cool, red is warm, yellow is hot, used to place hot tile sets. So they're basically using height to determine temperature as well. I mean, that looks amazing, doesn't it? That's a bit extreme with the blue and stuff, but that looks awesome. So yeah, it's just a way of it's like I say, it's like a debugging tool basically. And I assume that these, like the green bits, effectively become the volcanoes. The actual proper volcano where there's loads of cliffs on it. And then the other bits are where the lava is. And I say this goes back to my point above, where like here, that yellow and orange, they must have the same height value, and that they're chopping the top of the volcano off, and this will be where the lava is. So what they've done then is they've used a separate heat map in order to say, right, well that's hot, and therefore when it must go over a certain value, it must become lava. So that's the answer to my question from earlier, is that these are the same height, but this is hot, so it's lava, and this is not, so it's the dust stuff that they were talking about. So there you go. There's the answer to my question. The way it works is still a bit hacky because it runs as a mod and not part of the game engine. Essentially, it gets all the tiles in the game, changes their map colours to different values from black to white, or blues to reds, or to greens, and then it reassigns those tiles to only appear somewhere based on the noise expression you are trying to visualise. Using blue for values below 0 and other hues above 0 is very useful for elevation because that makes the 0 line transition very clear, and that is important because that tends to be our coastline. You can't really play the game like this, but it's invaluable in the early stages of a new planet or when trying to debug something. So naturally, when I started making planets at Wooby, I updated my tools so I could use them for Space Age. I'm pretty confident in saying that with these tools I can work on planets 10 times faster. Not only that, but Genhis and I have been working on some fancy new noise functions that we will reveal along with a new planet later. The new functions have a lot of settings, and trying to get them to all work without my noise tools would have not been very fun. In fact, I have my doubts that we would have been able to finish all of the features in the new system without some way of seeing what we were doing. I'll release Noise Tools 2.0 when the expansion is released. Map generation in C++ by Genhis. Okay, so I said earlier on, I'll give a warning when this got super technical. I'd say it's been fairly technical so far. This goes proper programming and code and etc. I'm not really going to explain it. If people really, really wanted to, I could probably dive into some of it. Some of it I don't understand. It's a long time since I did any code, and this is a particular area that I'm not that experienced in, if at all. So I could do if people really, really demanded it. But basically, I'm kind of just going to read this section. So there'll be time codes in the section below. In the description, etc. So if you want to skip ahead to something, then please do. So there won't be so much kind of speculation and discussion. I'll just run through this. When the first Volcanus map generation overhaul was merged, we noticed a significant slowdown as we launched the game and generated the planet terrain. This would have been a mild inconvenience for players, but launching the debug version many times a day made it very noticeable. So we would either have to give up on fancy map generation or spend some time to make it faster. Map generation already runs in multiple threads where possible, and we try to optimize the code for simmed execution, single instruction, multiple data. Runtime map generation is therefore efficient enough, which generally matched what we observed about Volcanus. The issue had to be somewhere else. As I dived deeper and deeper into noise expressions, I found some areas for improvement. In C++, noise expressions represent an abstract syntax tree, or AST, of mathematical operations. Each noise expression is a class instance storing its children. If you don't know what that means, just think of it as a bag that can contain other bags. They can be combined and nested up to hardware limits. The structure is fully built from its Lua counterpart. When a surface is created, noise expressions are compiled to a noise program. In general, each named noise expression is a procedure in the program. Procedures are useful because we can reuse data from multiple steps. The procedure contains a linear sequence of noise operations with already resolved dependencies, so it is guaranteed that children of a later operation have already been computed. This structure is optimized for fast computation when you need all data, so changes like short-circuiting if statements can't easily be done. Additionally, before noise expressions are compiled, they are recursively simplified. If all their children are constant, they can be folded into a constant as well. This step can't be done sooner because some variables depend on map settings. We've then got a diagram showing the noise expressions lifecycle in 1.1. I'm not really going to read these through again. As I say, I'm just kind of presenting this as presented. As I say, what they're effectively talking about is the way the noise is done is it has all these different functions in it essentially, and a lot of it is like procedural basically. So it's like do this, then this, then this, then this, then this, and that generates your noise. Okay, and if you think about what we were talking about above with the the sine wave and doing the absolute of it and then flipping it around and then adding the offset, that's like an algorithm. That's a procedure for generating that type of map function. And the point is that that's fine, and it's computationally simple because it's all it doesn't require going around basically. But basically, it therefore means it takes time essentially, and that's what they were noticing, that every time it's doing that noise generation, it's going through that procedure of generating that algorithm of that output and providing the output. And there are things in it where clearly, when it said above where it was talking about, you do a function that's a doubling of a function. Well, if the function you're doubling is 0, then you're always going to get 0 as an output. So you don't need to have that function in there, but you can't know that until you've done that once. Until you've done that calculation once, you don't know that it's 0 and 0, and you can just replace it with a constant. So basically that's what they're saying, that it's doing a lot of this maths and a lot of this process, and it's computationally simpler, but it takes time, and that's what they were noticing. Or I think it is anyway. Optimizing the internal structure. The system wasn't expected to be pushed to its limits, so the code didn't deduplicate identical expressions and instead allocated them separately. The base game allocated 31,000 objects and Volcanus even more at 280,000. I added a global storage which cached expressions based on their hash and could retrieve one without constructing the full object first. It reduced the number of objects to 5,300 and saved us 125 megabytes of RAM. Having so many duplicate expressions surely means there are other pieces which didn't reuse things, right? For example, the simplification step. When it found an opportunity to apply constant folding, the whole branch of the AST had to be recreated to replace one expression with a constant. This step created many temporary objects, almost as many as the number of permanently allocated expressions, 200,000 on Volcanus. I wanted to merge this into the compilation step and simplify expressions just in time. My attempt was successful, and creating the Volcanus surface from the inefficient noise expression tree became 15 times faster. So my understanding of what they're saying there is that effectively, rather than kind of caching some things, caching some numbers, caching some results, it would like build out the whole expression again, only to discover that it was, a constant, and, compress it back down to a constant. So again, it's that you multiplied 0 by 2, well, it's just 0. And what it was doing was effectively redoing that whole process instead of just saying, oh, well, we know it's 0, basically. That's a very, very simplified version, I think. And I think that's right. I'm not 100% sure. I continue the refactoring having in mind that writing optimal noise expressions is hard. My goal was to make the compiler aid modders with the optimization step. Therefore, I tried to deduplicate expressions used in multiple procedures. The new system would extract them to separate procedures so that the results could be reused at runtime. You don't need to call noise.delimit_procedure anymore, it's automatic. However, it turns out that figuring out which expressions are used by multiple procedures is not easy, and issues started popping up. I would have to sacrifice compilation performance if I wanted to fully deduplicate it. Not only that, but requesting to run a procedure would be more expensive because cross-procedural dependencies were computed on demand. I guessed it wouldn't matter because it was still insignificant, but why do something inefficiently when we can optimize it and make the code simpler? I think that's saying that basically that multiply by 2 function wasn't really a separate function that it's calling, which would be sort of how you do normal code. It's embedded within the function, basically. So it's just duplicated. So that, multiply by 2 is a function in it, or step in the code here, and the exact same code is written in loads of other places, and it's not, cropped out as a function. The reason being that when you use functions, it is like more complicated because it has to call the function, basically. Or, it's a different sort of complexity to it. And because the compiling process essentially goes through and does all that maths once, that's the advantage that it's gaining. But from what they're saying, it's quicker, basically, from what they want to have that as a function, and it just calls that function each time. I think that's roughly what it's saying. So I decided to remove procedures altogether. Instead of one noise program per surface, we now have 3: tiles, cliffs, and entities plus decoratives. These parts were run separately and didn't reuse procedure results anyway. Runtime map generation saw up to 20% improvement, and noise program compilation was up to 50% faster, although results varied depending on complexity of noise expressions. Now you can think of a noise program as one procedure with multiple outputs, which has its advantages. There are no dependencies and everything is inlined. If an intermediate result is not needed anymore, the memory is assigned to another noise operation. So it's like a long C++ function with stack variables being optimized away, although a somewhat simplified version. Problems with the Lua format. The Lua noise expressions format was introduced in Friday Facts 207. Although many people claim it is pure magic and hard to work with, it offers great flexibility to modders and allows them to create unique and atmospheric maps. Despite this, it has some issues. When you dump the data.raw prototype table, you will notice that a significant portion is taken by noise expressions. This is because the format is very verbose, with each AST node being a Lua table. Creating so many individual strings and tables also impacts performance. If we didn't use Lua functions and metatables provided by the noise library, the format would look like this just to compute x plus 5. I'm not going to read out that code. I said it got very techie, didn't I? Not readable, is it? Imagine chaining it 100 times with other functions and operations. The noise library hides this away, but the performance penalty and mangled output are still there, so we decided to change it. I was tasked with making the format read like math. That is, to create a parser which could process string expressions into AST. So just to explain that one, I do know that one. A parser, if you imagine an equation, okay, like we had the one we had before where A equals B plus C. A parser is something that will take that written text, so A equals B plus C, and turn that into an actual math expression. So you can literally type out A equals B plus C, and the game will read it in and go, right, well, I mean, you have to define what A, B, and C are, obviously, but right, well, plus means we take the number that is B and the number that is C and add them together, and then equals means that the number that is at the a variable that is A equals the result of that operation. And it basically converts that text string into a function. Yeah, so you don't have to write it as a function, so these x's and 5s and all this sort of stuff. Instead, you can just literally type out A equals B plus C. So long as you've defined what A, B, and C are, it'll work. At first, I was fixated on saving as much performance as possible, which resulted in a monolithic design. Functional, but hard to test, maintain, and expand further. Then, I started reading about how other parsers do it. I even considered using an external grammar tool which would generate the parser, but I didn't think it would be worth the time to learn using it, and the produced code would likely be suboptimal. In the end, I decided to go for an in-house solution. The parser was split into 3 logical parts. 1. A tokenizer, which processes a stream of characters and categorizes individual character groups to token types. The operator character set is based on Lua, with a few expressions where both C++ and Lua syntax are supported. Apart from regular numbers, it supports scientific notation, and other formats can be added as needed. That's what I'm saying basically about converting. So the plus symbol, it's just a cross really, but basically the syntax, C++ and Lua understand it to be a particular thing, or you can convert it easily into a particular function that they can both use. And the scientific function would be like squares and square roots and things like that. There are sort of standard ways of defining those. Well, not square roots because it's just a square that's inverted, but yeah. So there are different types of functions. Logarithms, I guess, would be one, and that sort of thing. Postfix tokenizer, which converts infix tokens to postfix reverse Polish notation. This step is responsible for following operator procedure rules and for making sure that resulting expressions are unambiguous. It uses a modified version of the shunting algorithm to process data. 3. Noise expression parser, which takes postfix tokens and converts them to a noise expression tree, AST. And this is just showing it in diagrammatic form, basically. So the Lua string, so just literally text that's written in Lua, is converted into these tokens, them being the individual bits. So basically it would understand that 153 as numbers 153 is 153 and not 1, 5, and 3, basically. The postfix and AST bits, I confess I'm not 100% sure on. And the noise expression parser basically converts it into this noise expression thing. I wanted to move as much stuff to C++ as possible to avoid expensive Lua string concatenation. Therefore, I extended noise expressions and allowed defining naming noise functions as prototypes. I also added support for local noise functions and expressions which aren't exposed to the global prototype table. There's more I could say about these improvements, but it would better fit a modding documentation or wouldn't make an interesting blog post. So now all noise expressions are passed from string, and the legacy format, which uses Lua tables, is removed for 2.0. Regarding the original issues, this was all done for. Noise expression takes 50% less time during prototype initialization, and the prototypes now load 20% faster as a result. I think we can all understand that bit. It's better, basically. Further work. My journey to improve map generation doesn't end here. The introduction of prototype-defined noise functions means that AST contained constants which didn't have any effect on the result and were quite frequent. I implemented partial constant folding using arithmetic identities, so expressions like 1 times x plus 0 are folded into x and aren't evaluated for every chunk. So 1 times anything is just the number itself, and plus 0 is going to have no effect. So 1x plus 0 is just literally identical to x. So it's basically saying if you find functions like this, then just replace with x, essentially. In addition, I noticed we hadn't been using basis noise, our Perlin-like noise function, efficiently. Its special case, x equals x and y equals y, is optimized because we know we work on a grid. We can reuse intermediate tile values, so it is 5 times faster than the generic implementation. When we wanted to offset the grid using x and y parameters, it would no longer be interpreted as the special case. Adding separate offset parameters improved the performance further. In other words, because they were offsetting, it wasn't using the x equals x, y equals y optimized version, because it was thinking it was a different thing, and all they were doing was literally taking that exact same grid thing and punting it over. So it should have just used that optimized special version with an offset. Instead, it was taking it to be a special function, and so doing it, as a complex calculation. I said I wasn't going to explain this stuff, didn't I? I'm getting carried away. I did more work around map generation, but not everything fit into the blog post. For example, I removed noise layer prototypes, added more noise functions, and made a few other tweaks. However, I had to make some compromises. Some noise functions were removed, including array construction. It is possible to add array support to the new parser if requested, although there are more pressing issues right now. The results. Several iterations have passed since the first Volcanus generation prototype. Its individual noise expressions have been optimized as well. Together with C++ improvements, what took 18.35 milliseconds per chunk now takes 2.83 milliseconds. This is a result we are quite happy with. That's a massive gain. I mean, that's, 9 times as fast? I'm sure you want to know how all this compares to 1.1. Base game initializes prototypes 7% faster, and in 87% less time is spent on noise expression prototypes. Now this noise programs are compiled 85% faster. Thanks to procedural removals, there are fewer noise operations. 6016 drops to 2233. This brings us 25% faster chunk generation on average, from 4.8 milliseconds to 3.58 milliseconds. All in all, around 90% of the noise expression engine was rewritten from scratch. I estimate I spent around 4 months working on the C++ side of map generation. It was well worth it because not only do we have a faster system, but also it is more maintainable and we can easily add new noise expression types as we need them. So it made it a lot more modular basically. Designing it was a fun challenge. The system may be a bit over-engineered just for map generation, but at least we have a solid foundation which we could reuse in other projects if we wanted to. It's that time of year again, by Erendel. Well done, you made it to the end. Merry Cogmas. We then got a little picture, basically a Christmas tree with red and yellow science as the bauble type decorations, and it's got a ribbon going around it, and the Factorio cog on the top, and everything is covered in snow. I don't know if this is, I don't think it is, but I don't know if this is some kind of hint about, we know there's a cold planet coming, so I don't know if we're getting graphics. I'm sure it's just been made for this, just for this Christmas. But it does make you wonder whether we'll get, snowy graphics or something like that. And so I don't think they'd be these because part of this is that the belts aren't moving. So they're obviously acquiring snow. And this is I think this would be quite confusing to try and play in. But it does make me wonder if we will get like an icy version of some of the graphics for this, winter, this cold planet. It would be quite cool. But as I say, this is probably a bit extreme. And I do like, the level of detail on this is amazing. I couldn't spot any Easter eggs, but actually they're good at spotting them. If you see any, then please do, please do let me know in the comments. We've got, oil derricks and pumps and belts and pipes and beacons and stack inserters and all sorts of gubbins going on. A lab. So yeah, there could well be something hidden in here. I could not see it though if there is. As I say, please do shout if you recognise anything. I assume this one is making, because you see it's got an inserter here, so I assume it's making something like low density parts or something like that for rocket parts maybe. It does look great. I wouldn't mind playing with skins, basically. And I've said this before, I know they don't want to do anything like that, but if they did do skins for the game, I would happily buy them. So I've spent so much, time that I've enjoyed in the game that I'd more than happily do a microtransaction to do a winter skin and other things. Make some noise and express yourselves in the usual places. So yeah, as I say, really, really techie one. I don't have a lot to speculate about. I say the only thing that I spot that looked weird was up at here, which was this orange, and it could just be copper. It's orange, so it could be copper, but it didn't look like copper to me. But that's, it's so thin as a point. These don't appear to be anything new in terms of terrain or, types and stuff like that. I hope the, explanation of the simple stuff was okay. And if people did really want me to try and dig in on the other stuff, I'd have to learn what it is kind of the problem, because some of it is new to me. I do love these, as I say. I'd happily... I don't think you could play on it. I think it's a bit extreme, but maybe I'll download the mod and use it to, generate some of these and have them as a wallpaper background or something like that. So this one in particular, I think would be really quite a good background. So I guess what I could just end on the video is just making a note that I am going to be working on a script to do possibly 2 videos. Maybe it'll just end up as me writing one over the Christmas period, which will be a kind of realistic speculation and a mad speculation is what I'm aiming for. And the idea will be me trying to predict what I think will actually come into the game, and what, if I was having my dream scenario of like the dream mod or something like that, what I would want to see in the game. When it's actually released, I'll hopefully then do a video sort of saying what I got right and what I got wrong. Some of it, I'll be honest, is kind of obvious, or as it's just Easter eggs that they've put in that we just don't know what it is. But we can take an educated guess, so we can see, did I get close with that educated guess? But yes, as I say, that's kind of the plan for over the Christmas period. When the video will actually come out, I don't know, because it'll have to be a sort of a proper edit. I don't know what I'll do for a background, for example, for the video. But yes, look forward to that coming over the Christmas period. I assume we will get a Factorio Friday Facts next week, because it is, a working Friday in a sense. I'll be taking holiday, but, I'll be back from my family for then. So I will do the Friday Facts next weekend. My guess is it'll probably be a simple one. It'll probably just be a picture tease or something like that, which might be a good jumping off point for some speculation. But yeah, we've had quite a few just recently that haven't really lent themselves to speculating. Ones like this, the technical ones, I do find absolutely fascinating myself, but fully appreciate it's not everybody's cup of tea. So yeah, it would be nice to get another one with big hints, in the new year, I think, about what's coming, or diving in on a new planet. And, we know nothing about biters yet, new biters. So yeah, there's a lot to look forward to. Hope you enjoyed today's Friday Facts video and might consider coming back for another one. If you want to chat about the latest Factorio Friday Facts, then you can find me live streaming Factorio every Saturday over on my Twitch channel @Trismegistus. Thanks for watching. Cheers. That's why it's called a square.